Audio test 1, 2, 3.
Test 1, 2, 3, 4, 5. Check 1, 2. One, two, three. Test 1, 2. Check. Test 1, 2, 3. One, two. One. 1, 2, 3. Check 1, 2. Audio gain has been adjusted. Audio down a little bit more. One, two, three. 1, 1, 2, 3, 4. House. That's house. Test 1. 1, 2, 3.
Yeah, yeah. No, it's fine. It just influences how much I'll be wearing my. I didn't realize I could still hang out. I didn't think so. What were you saying? I'm just messing with any mess, but like, still hanging out. I didn't realize like people are leaving for home like so soon in the day.
Oh yeah,
Like
it's like
we're done at noon.
all over. Yeah.
Are you half day?
No, I don't. I mean, I signed up for it, but
I'm not sure if they. I'm not sure.
like I think I'll sell all my stuff too. Stay. Or staying at the Airbnb or move. Yeah. I probably won't because I see Airbnb. There's a drum that runs screen in the room where we're on the screen.
I know it's weird seeing stuff.
So I go,
Oh, whoa.
Hi, Steve. Are you online?
Yes, I am.
Okay, great. Do you have a webcam, or will you not be turning that on?
I'll try turning it on.
Okay, that's great. Also, you can go ahead and share your screen, your presentation, and we can see if that's working.
Okay.
Okay, that looks great. And let's see. I think we're all good on this end.
Okay.
And so we're going to start at the top of the hour. So we have
Yes.
another 7 minutes or so.
Okay.
I've never like been like chair of a session before, so I assume you just introduce the people, but I don't really know exactly what you're gonna. Yeah, exactly. Right. Yeah. Right.
And then for any question and answer, we have this little catch box that we can pass around in the audience.
So that will stay on the whole time.
Yeah, I'll just keep that on. And I just I think I have it on now on the program.
Okay, perfect.
But then anything you want to pass around, catch. And so let's see. Test 1, 2.
So that's just the toggle button.
Check microphone 2.
Yeah, it might make most sense to do it that way. The only other way is maybe to toggle back and forth. So.
I think it's easier just to do.
Yeah. Yeah. And that would just kind of be a. Well, maybe we should.
Well, I think it's supposed to be 12 minutes for the talk and 3 for questions. Yeah, just 2 and 1.
Yeah, yeah. Yeah, so 10 minutes. Yeah, it's 10 minutes. Do you know any of his
I know Steve. Well, I've never met him, but
Is
he's
it,
a big deal.
I guess it's for Lunar.
Yeah, I'm pretty sure it's for yeah, like our like team for Untitled is all about culture. I guess mostly. I guess it's for science stuff.
So then you're in Colorado?
Yeah, this is critical. Yep.
I guess, all right, let's see. I mean, which is always good.
It might not be for your initial project.
One thing I forgot to mention is the slide advancer for the other presenters. Just basically forward, back, forward and back, and then this is a highlighter button that will
Oh, yeah, I saw that.
highlight,
Yeah, I saw
spotlight
that.
the section that you want to point at.
Okay.
And so Stephen's, so I should just be able to introduce him and he'll start speaking.
Yes, and you'll probably actually turn on his camera, and so yeah, we'll be able to. Yeah, so he can hear you right now.
Okay, perfect. Okay, in an effort to keep us on time for the USS Hornet, I'd like to welcome everyone to the Science from and of the Moon parallel session this morning. Our first speaker is going to be giving his talk remotely. This is Steve Ferlinetto, and he'll be talking about the insights into the first stars from low-frequency radio observations. And go ahead, Steve.
Can't hear you, Steve.
Thank you. Apologies for not being able to be at Ames, but thanks to the organizers for letting me dial in. So today I'm going to be talking about what we can learn about astrophysics from what we have learned, or sort of learned, from the ground, but hope to learn more about from the moon soon. So I'm basically following up on Jack Burns' talk yesterday about cosmology from the moon. This is a sort of orientation slide showing the timeline of the universe with the Big Bang at the left to the present day at the right. And there are a bunch of important epochs shown here. Near the left is the recombination era. That's when the cosmic microwave background was last scattered. And the important point for this talk is that that means that after that point, the universe became neutral. It remained neutral for about 13.5 billion years, or 12.5 billion years, excuse me, until enough stars had formed and produced ionizing photons to render that gas, render the intergalactic gas ionized in an event we call reionization. And that happened about 1 billion years after the Big Bang, or about 12.5 billion years ago. That is just about also the limit of our current understanding of galaxies. So we can study galaxies in detail out to the present day. And as I'll show in a moment, we found them through the sort of end of this reionization era. But out of our vision so far is the formation of the very first stars and galaxies in the universe's history. And that's an event that we call the cosmic dawn. And it's extremely important for understanding the origins of complexity in our universe. So that's where what we're trying to learn, and where we'll get to soon. But so far, what we know about these early generations of galaxies come from pretty traditional astronomy measurements. You look at a blank patch of sky and you try to find very faint, distant galaxies. So the Hubble telescope and soon JWST do this. And HST so far has helped us kind of measure the abundance of bright galaxies out to about 500 million years after the Big Bang. And for the purposes of this talk, the important result of that is simply that those galaxies behave very similarly to galaxies at the present day. Okay, so on a big picture level, we can understand them with the same kind of models that we use for normal galaxies later on. Unfortunately, even with JWST, we are not going to be able to push back to the era of the very first stars. So we want new probes to be able to do that, and one of those is the spin flip, or 21 centimeter transition of neutral hydrogen. So this comes from the electron spin changing directions, and because of the magnetic interaction with the proton spin, that produces a photon with a wavelength of 21 centimeters. However, this photon would have been produced in the early universe, and as the universe expands to the present day, it will have, its wavelength will have increased of order 10. And that means that we're going to observe these photons to have frequencies of 20 to 200 megahertz or so if we're studying this early cosmic dawn era. And as it turns out, that's a very difficult regime to observe from the ground, and that's the main reason we would like to go to the moon. I'll get back to that later. Okay, so now I want to kind of show you a history of the universe in this spin flip transition. So the left panel here is showing a snapshot of a simulation of what this transition would look like at various times. And the right panel is showing the average intensity of the signal as a function of time or observed frequency. So the left side of that right panel, low frequencies, corresponds to early in the universe's history, and the right side will be relatively late. So we're going from before the formation of the first stars here to this reionization era 1 billion years after the Big Bang, okay? So before the first stars formed, the universe is a pretty boring place. And so I'm guessing on your screen, you just basically see a green. There are tiny little blue splotches there, which are just density fluctuations growing in the universe. And these are before the first stars. So the only thing that would change the signal here is some exotic physics, dark matter, black holes, stuff like that. As time goes on, this early signal fades away, and until the very first stars form. When those first stars form, they flood the universe with with ultraviolet photons, and those photons turn on this 21 centimeter signal, and they turn it on in absorption. Okay, so in the snapshot, you're seeing little blue patches, and those are regions around these first stars that are being illuminated, and we're starting to see them show an absorption against the cosmic microwave background. That will persist until the remnants of these first stars produce X-rays, okay? And those X-rays flood the universe and start to heat the gas and turn it from absorption into emission. So now the red splotches in the snapshot are regions near these first black holes that have been heated. The blue are regions that are still being heated, okay? But eventually the whole universe is heated, and we see this signal in emission against the cosmic microwave background now. And the last thing that happens is those first sources produce ionizing photons, which destroy the neutral hydrogen, right? And that means we don't see a 21 centimeter signal from the black patches at all. And as the whole universe gets ionized, the signal fades away, okay? So there's a rich astrophysics in the signal, and the really cool thing is that it's sensitive to the entire radiation background of all of the stars in the universe, even those in sources that are so faint we can't pick them out with our telescopes. So this is complementary to like JWST observations, which will look at bright things. This will allow us to see the very faint things, and it allows us to push to the earliest stars to have formed. Okay, right now is a very exciting time for this because about a year and a half ago, Judd Bowman and the EDGES team announced the first detection of this 21 centimeter signal. Right, so this is their data. What they found was an absorption trough about 200 million years after the Big Bang, okay? And as I'll discuss, there's very confusing aspects to the signal, and it is very controversial. So what I want you to do is, I'm going to tell you how we interpret it, but at the very least, that's an example of what we can learn from similar lunar observations in the future that are hopefully less prone to contamination. All right, so now the right panel here is showing this 21 centimeter background again. The kind of gray band is a mock-up of that EDGES detection. And the black curve is showing what we would predict this signal to look like based on our models of the galaxies we can see. Okay, so the left panel is showing the galaxy abundances that we can measure along with fits to them, right? And as I said, simple models reproduce all the galaxies that we can see, more or less, at least the gross properties of them. So what we've done is take those simple models and just extrapolate them to earlier times. And what happens is you do not fit the EDGES signal, right? You get three things wrong. One thing you get wrong is the shape of the signal. The observation is too narrow, okay? I'm not going to talk about that again because that's sort of the least interesting of these problems. The next thing you get wrong is that the predicted signal is not deep enough to match EDGES. So remember, the prediction is the solid black line here, okay? I'll get back to that depth later. For now, the dashed line just says, well, we got the depth wrong, let's make it deeper. Even if you do that, though, you can see that it doesn't match up in frequency, which corresponds to time, right? So the prediction of the galaxies we can see does not start the signal off early enough. If we want to fix that, what we need to do is make more stars early in the history of the universe, okay? And there are two ways to kind of think of doing that. One is you simply say that at early times, galaxies produce stars more efficiently. Another, slightly more sophisticated way is to say that, well, we've only seen the very bright things. So you could imagine making the star formation more efficient in small clumps of stars. We haven't seen those yet, so we can't rule that out either. And that works because at very early times, only small things are around to form stars, okay? So in this panel, I've done the second, which is make star formation more efficient in small halos, small clumps. And the problem is on the right, you can see that when you do that, you no longer match the observations of the abundance of bright galaxies either, right? You start to get into a regime where things are conflicting, okay? So the bottom line is what this EDGES detection tells us is that you need to make stars more efficiently in small or early things. And that's the first hint we've ever seen for star formation working in some exotic way, okay? And that's exciting in light of this cosmic dawn era because we expect the very first generations of stars to form in exotic ways, okay? Normal present-day stars form, they need to cool in order to get to the high densities to start fusion, okay? And the way they do that cooling is through heavy elements. But heavy elements weren't created by the Big Bang. And so the first generation of stars have to work differently. And it turns out they probably are more massive, okay? So now let's think about, can these exotic first generations of stars help us to understand edges? And the answer is yes, okay? So this is some work, ongoing work by my graduate student, Rick Mebane. And what he basically did is built a model of these exotic population 3 stars and predicted the 21 centimeter background from it to see if we could match the edges detection, right? So now these panels are showing the edges detection as the light gray, and the different curves you're seeing are different implementations of our model. Okay, so we've never seen these population 3 stars. We have little idea what they're really like, so one can make a variety of assumptions about them, and our model is built to allow for all of these different assumptions. But the important thing that happens is that in a wide variety of those assumptions, we more or less get the timing right for this signal, okay? So it's not unreasonable to think that population 3 stars can fix one of our problems, right, and push the signal to happen earlier, to turn on earlier. Now there's that second problem, which is that we didn't get a deep enough signal, okay? Can we fix that? Right? Well, that's harder. So it turns out that the depth of the signal, in order to get it large enough, you need to do one of 2 things. The first thing you could do is make the gas colder than you expect from an expanding universe. That requires exotic interactions with dark matter, basically, okay? If that's the case, then those exotic interactions should be happening before the first stars form as well. And so you would see changes in the very, very low frequency side, and you can study that with Dapper or other lunar arrays. The second thing you can do is say that, well, the gas is the temperature we thought it was, but it's absorbing against a brighter background. That could be a bright background generated by exotic physics, or it could be, maybe it would be great if it could also be generated by the same population 3 stars that are fixing the timing, okay? So we also used Rick's models to look at that. It turns out that, as you can see in the cyan curve in the top, you can write down models that reproduce the depth as well. However, it's not easy. Okay, you basically need to fine-tune things in ways that we can't explain. So in particular, you need to make these first stars 50 times more efficient at producing radio waves than they are at anything else, and than local comparable sources are. Okay, so it can be done, but it seems unlikely. All right, so that's kind of where we stand in understanding the 21 centimeter signal right now. Again, we're not sure that this hasn't been confirmed yet. Okay, so this is all very preliminary inference. But the moon is great because it's going to allow us to follow this up, both at lower frequencies, and that will allow us to look before the first stars form and separate kind of this exotic physics from astrophysics. And second, to study the cosmic dawn era with much cleaner systematics. The moon is a much nicer, has much less interference, has no ionosphere, and so it's easier to interpret the observations there. So with things like Dapper that will study this global signal, we can do it better than we've been able to do it from the ground. And in the future, with Farside and the lunar arrays that it might grow into, we can start to actually study different aspects of the signal, like those maps that I showed, instead of just the average intensity, which will teach us a lot more about astrophysics as well. All right, so I will stop there. I think I'm probably out of time. But thank you again for letting me call in remotely.
Okay, thanks, Steve. Does anyone have a quick question for Steve? You have the speaker that we can share around? No questions? Okay.
Hello, Alex Hedges from University of Michigan. You say that in order to, one of the fine tunings that your model does to match the results is to have 50 times more efficiency in creating radio waves for the first stars. Does that imply a breakdown of like the black body emission spectrum, and how would you reconcile that?
So these are the radio waves would come not from the stars themselves, but from their remnants, the black holes. So these are probably very massive stars, and so under certain mass ranges, they leave relatively massive black holes, and then those black holes can accrete gas. During that accretion process, in local sources at least, you get lots of fast electrons, and those electrons produce synchrotron emission and inverse Compton. Okay, so you get a non-thermal spectrum to begin with. The problem really is that the synchrotron emission has to be much more efficient to produce these enough radio waves. However, the same sort of non-thermal electrons magnetic field system would also be producing higher energy photons, X-rays. And if you crank up the radio waves by a factor of 50, you might expect also to crank up the X-rays by a factor of 50. But if you do that, the lower panel here shows that you also kill the signal, right? So you need to increase the non-thermal processes that make radio waves without increasing other non-thermal processes, which is why I think it's hard. It's going to be hard to arrange. I'm sure it can be done, but it's a fine-tuning kind of thing.
Weird. Thank you.
Okay, let's thank Steve one more time. Okay, I'd now like to introduce my co-chair, Neil Bassett, who will be giving the next presentation entitled The Radio Quiet Environment Above the Lunar Far Side and Its Application to 21 Centimeter Experiments.
Thanks. So I'll begin with a kind of overview of 21 centimeter cosmology. So this is probably going to be a lot of the same things that you just heard from Steve, but it never hurts to hear it again, especially if this is not your field, because this stuff can get confusing. So the 21 centimeter refers to the rest wavelength of the hyperfine or spin flip transition of neutral hydrogen. And so we can use this transition to really probe the neutral hydrogen that existed and the conditions that were present in the early universe. So the rest frequency of this transition is 1.4 gigahertz, but because of the expansion of the universe, the radiation becomes highly redshifted, and so by the time it reaches us, we see it in between about 10 and 100 or 200 megahertz. And because we're looking at a single transition, if we take a spectrum, each frequency corresponds to a different redshift or a different time in the universe. And so you can really read the 21 centimeter spectrum as a sort of history of the hydrogen or the evolution of the hydrogen in the universe. And so in this 21 centimeter spectrum, we expect to see two different absorption troughs relative to the cosmic microwave background. So the first at lower frequencies is the dark ages trough, which corresponds to the time before any luminous objects existed. And at higher frequencies, the cosmic dawn trough, which corresponds to times when the first stars, galaxies, and black holes began to form. And as Steve went into, just last year, the EDGES team published the first ever detection of the cosmic dawn absorption trough. And like he said, this caused quite a stir within the community because the characteristics of this absorption trough were quite different than those predicted by the sort of standard cosmological model as we understood it previously. And so another reason that this detection was so groundbreaking is because doing this, observing the 21 centimeter spectrum, is extremely difficult to do. So in order to see the 21 centimeter signal, you have to look through extremely bright galactic foregrounds. So that's the black line in this plot, which are about 4 to 5 orders of magnitude brighter than the actual 21 centimeter signal that we're trying to see. So fortunately, there are some key differences in the characteristics between these foregrounds and the 21 centimeter signal that we can leverage to kind of pull them apart and extract the 21 centimeter spectrum specifically. And so this is already just a difficult problem of extracting these two different components of the data. But if you're doing a ground-based experiment, you also have to deal with ionospheric effects. So the ionosphere is the upper ionized portion of Earth's atmosphere, and so any sort of radio waves at these low frequencies that we're trying to observe, when they pass through the ionosphere, they're going to refract, they're going to be attenuated, which can contaminate our observations. And so the plot that you see on the right here is the amount of attenuation caused by the ionosphere as a function of frequency. And so this plot only goes down to about 40 megahertz. But you can see that as you decrease in frequency, the amount of attenuation increases. And so the effect is that below about 30 megahertz, which I'll remind you is where the dark ages absorption trough in the spectrum resides, the ionosphere essentially becomes opaque. And so doing these observations from the ground is really not possible. And so as if the ionosphere wasn't a big enough problem, we also have to deal with radio frequency interference, or RFI. So this data comes from, was taken in a location in Europe, which was a possible site for LOFAR, which is another low-frequency radio experiment. And so you can see that below 30 megahertz, there's all kinds of terrestrial radio communications that we're going to pick up with any sort of low-frequency radio experiment. And so this can also contaminate our data. And so the result of all of this is that in order to perform these very sensitive low-frequency measurements, we really need to go to a location that's both above Earth's ionosphere and to a location where the RFI from these terrestrial sources is blocked. And so really the only candidate that's a feasible location to do these experiments is from the moon. And so if you remember back to your first year physics class, when waves hit any sort of boundary, they're going to bend or diffract around the edge of that boundary. And so the same is true for the problem of RFI and the moon. So the RFI is going to bend around the edge of the moon and create a sort of cone behind the lunar far side in which these radio waves from Earth are heavily attenuated. And so I'll emphasize that this is different from the geometric cone, which would be behind the moon, just considering the simple geometry of the system because the Earth is larger than the moon. However, because of diffraction, this region will be smaller in size. And so we really want to get a good idea of how large this radio quiet zone is so that we can get an idea of where we could do these experiments. So unfortunately, this problem of diffraction around a spherical object in the near field does not have an analytic solution, so we really need to turn to some sort of approximation first to try and get an idea of how much attenuation there should be. So the most simple approximation we can make is just simply saying that there's a knife edge or a straight edge at the location of the moon and see how much diffraction there is around this edge. And so this problem was solved analytically a long time ago, but more recently there was a paper published in 2007 which applied this approximation to the case of RFI and the moon. And so here they're plotting the relative intensity of the RFI as a function of angle behind the moon. And so you can see that this middle line here, the dotted line, is 100 megahertz. And so directly behind the far side at 180 degrees longitude, they're saying that there's about 70 dB of attenuation of these radio waves. So that's a good start, but there's reason to believe that this approximation is not a very good one. So for one thing, it's just an edge, so it's assuming that there's just free space behind the edge where the diffraction is happening. And also, it doesn't take into account any sort of electrical properties of the moon, which might affect the amount of diffraction at different frequencies. And so in order to get a better idea, we need to move towards some sort of numerical computer simulation. And so one of the more popular algorithms for doing electrodynamic simulations is called a finite difference time domain method. And so really all you need to know is that the nuts and bolts of this simulation is that we're discretizing Maxwell's equations onto a finite grid. And the way that we do that discretization, we're actually calculating the electric and magnetic fields at slightly offset grid points and time steps. And then when we want to output our results, we can interpolate the fields onto the same grid to make sure that they're consistent. And so I applied this simulation technique to the case of the moon and RFI. So this is a 2D simulation that I did. And you can see that on the left is the RFI coming from the Earth, and then on the right is the far side of the moon. And you can see that just by eye, you can see that the radio waves are heavily attenuated behind the far side. And in order to kind of try to capture the electrical properties of the moon, I took some kind of average values for the properties of the lunar material. And I just used average values because we're really not concerned with how far the waves penetrate into the surface. We're more concerned with their intensity behind the far side. And so we can use these simulations and apply it to the two different cases of possible places we could do these experiments. So the first would be actually to put an experiment on the lunar surface, and then the other would be to use some sort of satellite in orbit around the moon and to do the experiment from there. So these plots are showing the intensity of the RFI as a function of angle for these two different cases, both on the surface and for an orbit 50 kilometers above the lunar surface. And so these are done for a range of different frequencies. And I'll point out that I've put a dashed line at 80 dB because that's approximately the level of attenuation that we'd like to get to in order to do these sensitive 21 centimeter observations. And so you can see that as you move from low to high frequency, the behavior is what we'd expect. So at higher frequency, there's less diffraction, and so the radio waves will be more attenuated behind the far side because they're not bending around the surface of the moon as much. And so the amount of attenuation is becoming greater, and the width of the region at a certain amount of attenuation is becoming wider. And so one final thing I'll point out about these is that you'll probably notice in the labels that these simulations were done for kilohertz frequencies. If you remember the 21 centimeter spectrum, we mostly see it in megahertz frequencies. So the reason for this is that doing these simulations at these megahertz frequencies is extremely difficult computationally because of the amount of grid points that you need to compute. And so we started out at lower frequencies, and although we'd like to push these to higher frequencies in the future, we can really use these low frequency observations to place kind of a lower limit on the size of the radio quiet region, because we'll know it would be at least this large and even greater at higher frequencies. So the simulations that I've shown previously, I just used a perfect circle in the 2D simulations for the moon. However, we know that in reality, the moon has topography and craters on its surface. And so I wanted to investigate how this topography affected the amount of attenuation. And so these plots are similar to the ones you just saw for both on the surface and for an orbit above the moon. But now we're comparing the case where the simulation was done with a perfect circle in this 2D grid and the case where we actually used actual lunar topographical data in the simulation. And so you can see that the effect is small. It's really on the order of about a few dB, but especially above the surface, you can see that craters tend to create deconstructive interference, and so the amount of attenuation is slightly greater, even if it is a small effect. And so I'll finally close out with this projection of the lunar surface, and I've marked out a few different locations which might be possible locations for some sort of radio experiment or radio array on the lunar far side. And I've also marked out a region where we have at least 80 dB or greater attenuation of RFI from Earth at 100 kilohertz. And I'll remind you that at higher frequencies, such as megahertz frequencies, this region will only be at least this large or greater because of the effect of diffraction. And so really what I want the takeaway from this talk to be is that there's a very large region on the lunar surface and behind the far side where there's sufficient attenuation of radio interference from Earth that we can perform these very sensitive low-frequency 21 centimeter observations from this radio quiet environment behind the far side. And I will just put up my conclusions and take any questions.
Okay, the talk is open for questions.
Can't get used to this box. The moon libration, what is it, about 11 degrees or so?
I don't know that I know it off the top of my head, but that could be right.
But that will blur that circle, won't it?
I'm not sure what you're referring to.
you're talking there in terms, maybe I've got it completely wrong. You're talking about straight line view from the Earth, straight line noise, if you like.
Which slide were you referring to?
That
This
one.
one? Okay.
Yep.
Yeah.
Is that going to be fixed or is that, sorry, as the moon librates, that will face noisier parts of the Earth?
Well, so I mean, the far side will always face away from the Earth. So,
but it comes around. Come on, Mahaley.
So I think I think this blue circle that is probably fuzzier because of the vibration.
right, sure, yeah, on the edges. I mean, if there's a slight
Okay.
tilting, then yeah, around the edges it won't be a perfect line. It would.
The
be
second question,
fuzzy,
the real
sure.
question I stood up is, Shanghai 3 or Shanghai 4 is already active there
Mhm.
on the far side.
Right.
Do you see any implications or any management that should be recommended?
Well, I mean, I certainly think as we move into a era of increased lunar development, we definitely need to be careful about preserving this radio quiet zone on the far side. So that's certainly something that needs to be taken into account, I think, when missions are planned for the far side. But as far as the single Chang'e 4 lander, I think that it's probably not a significant concern for any sort of surface experiments as long as you're not right next to it. I'm not totally familiar with the radio environment of the actual lander and how noisy it is specifically, but certainly moving forward, this is something we need to think about.
Hey, Jason McLean, NASA guy. I just had a quick question. Do you need the far side, you also need night time? And if that's the case, how long do you believe you will have to observe to get appreciable signal?
Yeah, so the sun is certainly something that we pick up if it was daytime on the far side, but we're really more concerned with RFI from Earth because it's much more unpredictable, and so it's really harder to model it and remove it from any data than like other sources.
Is your question very short, Mihai?
Very short.
Okay.
How about Jupiter?
Yeah, I mean, Jupiter is the same thing, that we'd also pick it up when it was, in the view of our observations for sure.
Okay, let's thanks Neil once again, and welcome our next speaker. So our next speaker is Joseph Samiango, and he will be presenting a talk entitled "A Double Hemispherical Probe for Improving Space Plasma Measurements."
Thank you. My name is Joseph Samaniego. I'm part of the survey impact at CU Boulder. I'm going to be switching gears a little bit from radio astronomy to space plasma measurements, specifically in situ measurements of Langmuir probes, and how we can and how using a double hemispherical probe you can improve the plasma measurements within the spacecraft sheath of the probe. So first, a Langmuir probe is a very simple probe. It's a conductor that's inserted into the plasma around the spacecraft, and from that you can get the spacecraft potential, the temperature, and the density of the surrounding plasma. The double hemispherical probe is nothing more than a Langmuir probe that is a spherical Langmuir probe that is split into two hemispheres that are electrically isolated from each other. The reason for this will become apparent later. So there's kind of that's the Langmuir probe. Now the spacecraft sheath is the main problem we're focusing on with this talk. Due to spacecraft charging, there'll be an area of non-uniform plasma around the spacecraft. This will cause a change in potential and create a change in density around the plasma. And this non-uniform sheath around this ruins a lot of the assumptions that are made when you attempt to analyze the probe, when you attempt to analyze the IV curves from the probe. So So when you put the probe inside of the spacecraft sheath, you see these purple lines here are the same that was shown before. And now you see the probe at different biases will have different potentials seen by either hemisphere of the probe. And these differences will cause a different flux of current to the probe. Specifically, the reason why we make this double hemispherical probe is to build an asymmetry in the probe that matches the asymmetry in the plasma environment around it. You see here that when the probe is in the bulk plasma far away from the spacecraft, the two hemispheres line up, and the current from the two hemispheres lines up quite nicely, and the addition of the two hemispheres matches if I would have just put in a single probe inside the plasma. As the probe moves deeper into the sheath, however, you begin to notice that not only does this red curve here, not only does the overall current the overall IV curve begin to warp, but also the current collected from either hemisphere begins to diverge. Now, the idea was whether or not we could use this diverging current in the saturation region to then gain some sort of insight, not only how far you are in the sheath, but if we could then use this difference to then reconstruct what the true plasma parameters are. So the first thing we notice is that if you looked at the saturation current, the area there where you had the divergence of the current of either hemisphere, we noticed that the ratio actually gave pretty flat lines, pretty flat saturation regions, which meant that it didn't really matter where you were in the IV curve as long as you were as long as you were inside the saturation region. Now, we plotted this current as a function of what we would call sheath depth. That is this potential profile here, difference between the local potential and the ambient bulk potential normalized by the Debye length. The Debye length is a characteristic length scale of plasma that shows screening. Now, when plotted all together, we found that there is a correlation between the ratio of the saturation currents gotten from either hemisphere and this sheath depth, and it formed a nice line. Now this was curious because that meant that we were now able to find a way of the double hemispherical probe could tell you effectively not only if you were in the sheath and whether or not you could expect errors in your measurement, but also how deep you were in the sheath using this metric. Now, that's only half the story. The second story we want to be able to do is whether or not we can use this probe to then come back and retrieve the true ambient plasma parameters. Now, we did that by, again, looking at the measurements as we move deeper into the sheath. I give you of the three curves, of the three plasma conditions, I give you, characteristic plasma measurements, I give you two, the temperature and the spacecraft potential here. And you see that also as a function of sheath depth, this phi over lambda, that they generate nice straight lines between the ratio of the measured and the true plasma conditions. This meant that we could fit a line to that, and because from the previous graph, we got a ratio between the current measurements, we could create a a experimentally verified curve that if there was a difference in either hemisphere in the current in the saturation region, then you'd be able to then figure out what how wrong your measurement would be. The idea was then that if we had this over a variety of plasma conditions we could then go backwards, and using this measurement, whatever we got from our Langmuir probes, we could work backwards then and find what the true measurement was. Now, so this worked incredibly well for the spacecraft potential, for retrieving the spacecraft potential and retrieving the true electron temperature. However, when we tried to apply this to the electron density, we found that there was no nice line as shown on the two left graphs here. It was garbage. And this is kind of because the density itself, when measured from a Langmuir probe, is itself a function of not only the current that begins to reduce as you go deeper and deeper into the spacecraft sheath, but also is a function of the potential, the plasma potential, in this case the spacecraft's potential, which also itself begins to shift as you move deeper into the probe. Now, however, we were still able to recover, use the double hemispherical probe to recover the local potential, and using that, we assumed that the density would fall off via Boltzmann distribution as you began to go deeper into the probe, as you begin to go deeper into the sheath. That is that if we had if we found the local potential, we could use the measurement of the density gotten from the Langmuir probe and work backwards. And from that, you see here, we were able to find some correlation here. However, it was roughly on the same order of magnitude as the air, same order of magnitude as if you were to just trust the naive plasma measurements. And no, if I have time at the end, I can kind of explain more of why that was the case. However, when you look at just the Langmuir probe measurements for the spacecraft potential and the electron temperature, we actually see a great improvement over the naive measurements. You see here that if we look at the retrieved spacecraft potential compared to the true spacecraft potential shown here, and the true electron temperature and the measured electron temperature compared to the true, we see that while the single probe analysis, the naive Langmuir probe analysis begins to drift as you go deeper into the sheath, as long as we're able to get an IV curve and measure characteristic features, we're able to retrieve the accurate plasma parameters much deeper into the sheath than a specific Langmuir probe, than a traditional Langmuir probe. So with that, I want to conclude by saying that the double hemispherical probe can not only tell you when you're in the sheath and when to expect errors in the measurement, but it can also tell you how deep you are into the sheath. And using the difference in the current, the difference between the saturation currents of either hemisphere, you can work backwards and retrieve the true ambient plasma parameters even when the probe is immersed in the sheath. Now, I do want to emphasize that this doesn't necessarily advocate for for shorter booms while using a Langmuir probe. It just means that the amount of plasma conditions that the spacecraft can be flown in, where you can trust your Langmuir probe measurements, increases. And with that, I'll take any questions.
Where's the speaker? Great.
Interesting analysis. May I miss this? Did you mention which spacecraft the two different measurements were made, and were they measured concurrently on the same spacecraft, or you're just trying to compare different environments from two different missions or multiple missions?
Yeah, no, my apologies. So this is all lab work. This is all this schematic shown here at the beginning shows a prototype, a lab model that is put inside of a plasma chamber. We create the spacecraft by floating a plate and allowing that to charge up, essentially mimicking the charging up of the spacecraft. And so the reason why the main advantage, and then these graphs. The graph on the right there is over the case of a bunch of plasma conditions. So it's not just one plasma case that we're simulating. We pretty much railed the plasma chamber on every end in order to try to duplicate as many space-like conditions as possible. And across all space-like conditions that we were able to create, we found that there was this trend.
Okay, so if this is a lab experiment, do you have a comparison with what a Langmuir probe or DHP on an emission has done?
So we're trying to get the DHP to fly on a spacecraft.
What about the Langmuir probe? I mean, they've flown on spacecraft.
Yes, they have.
So how have they matched up with your laboratory experiments with their data?
So Cassini is actually a good case of where we actually was an inspiration for trying to figure out what happens to a Langmuir probe when it's in the spacecraft sheath. They ran into issues with that, and it was kind of a work from them that seeded this work.
Okay, thank you.
Okay, any other questions?
Hey, cool experiment. I was just curious if this was all stationary plasma or if you actually had a flowing plasma, and if you do have a flowing plasma, would this method still work, or would you need to change something?
So this is this probe and sheath is one of 4 plasma environments that we hope that the double probe will improve on. So this is only the probe and sheath. The next case actually that I'm working on right now is a probe and a flowing plasma, and to see how the 2 hemispheres react in that situation and what information you can glean from that you wouldn't otherwise be able to get with a traditional probe.
Right.
So for curiosity, it's a probe and sheath, probe and flowing plasma, dusty plasmas, and then also with photo and secondary emissions from the spacecraft. So these are kind of 4 main projects that are under this global project.
Nice. Thanks.
Okay.
Any other questions?
Any further quick questions for Joseph? Okay, if not, let's thank the speaker once
Thank you.
again.
Okay, our next speaker will be Ariel Deutsch, who will be telling us about investigating diurnal changes in the normal albedo of the lunar surface at 1064 nanometers, a new analysis with the Lunar Orbiter laser.
Thank you. Is it possible to lower the lights in the front, please? If that's okay. Thank you. So today I want to talk about how the surface temperature of the moon may influence our measurements thanks of normal albedo. And for this analysis, we're using the Lunar Orbiter laser altimeter, which is also referred to as LOLA. So we know that the thermal environment on the moon is quite extreme. The moon rotates relatively slowly. It also doesn't have any appreciable atmosphere. And as a result, the temperature variations experienced in the equatorial regions can actually rise on the order of 400 Kelvin between midnight and local noon. And these temperature variations can cause important spectral changes in rock-forming minerals in the near-infrared wavelengths. So temperature variations can control the size and the shape of the crystallographic site, and this controls the position and the depth of major absorptions. So for example, here are a variety of pyroxene spectra that are plotted, that were collected at a variety of different temperatures, ranging from colder temperatures shown in blue at 80 Kelvin, increasing up to warmer temperatures shown in the red colors at 400 Kelvin. And what earlier lab studies demonstrated for these different minerals is that spectra that were collected at warmer temperatures have broader absorptions, again shown in the red, and then in contrast, samples that were collected at much cooler temperatures, shown in the blue, have narrower absorptions. So as these samples are cooled, the sites contract, and this actually causes an increase in the crystal field splitting energy, and as a result, an increase in the measured reflectance. This phenomena is dependent on wavelength, but curiously, one of the largest changes experienced by pyroxene overlaps with the observation wavelength of LOLA, which is 1064 nanometers. And we can take a look at how the temperature-dependent change occurs for certain minerals, specifically at LOLA's observation wavelength, and that's what's shown here. So on the y-axis, we have the measured reflectance for a variety of pyroxene samples in the orange, and then olivine samples on the bottom in blue. And these are collected over a variety of temperatures. So on the x-axis, increasing from colder at 50 Kelvin up to 400 Kelvin. And so what we can see is that over this temperature range that we're experiencing over the course of the lunar day, we have major changes in the measured reflectance of pyroxene, in fact, about 1.5 times. On the lunar surface, of course, it's going to be a more complicated story. There are a variety of other minerals that are mixed in the surface materials, as well as space weathering effects that actually dilute this strong temperature reflectance relationship. But earlier analysis of some returned Apollo samples by Henriks and Lucy demonstrated that about a 5% change was able to be detected in Apollo samples for temperature ranges that are coincident with variations in temperatures experienced over the course of a lunar day. So 5% variation is on the order of uncertainty for a single LOLA shot, but we've been observing the lunar surface now for about a decade, and we've been able to accumulate millions of individual observations of the lunar surface. And so the primary question that's driving our research is, how does the surface reflectance of the moon, as measured from orbit by LOLA at 1064 nanometers, change over the course of a lunar day, where we have these major temperature fluctuations? And we're interested in this question for two main reasons. One, understanding the distribution of important minerals on the lunar surface, but then also thinking forward to future observations of the lunar surface, really understanding how this temperature can control our measurements that we're able to take. So in order to tackle this question, we're looking at the normal albedo of the surface from LOLA. Again, this is at 1064 nanometers. And then we're tying that to the temperature of the surface as measured by diviner. And we're specifically looking at data that was acquired between local 0700 and 1600, because this is the time gap where we have coverage of the lunar surface from LOLA. We're binning the data in 1 degree by 1 degree spatial bins, which equates to about 30 kilometers, depending on where you are. And specifically from 65 degrees north to south, because this is where we experience the largest temperature variations on the moon. So first I'll show the normal albedo of the moon, and what we're looking at is both the far side and the north and the near side, and these transparency gaps are giving you a sense of the overall coverage we have by LOLA over the course of the lunar day. And so as we travel along the screen, we start at 0700, we travel through noon, and then we end up at 1500. And then on the bottom here, we have the diviner day of the surface temperature, again, stepping through time from left to right. And so the overall temperature variation that we're capturing in this in this group is about 100 Kelvin between 700 and local noon. And so one thing that I would like to start with is by looking at between 7 and 8 and then noon to 1 p.m. local time, because this is where we have that large temperature variation. And so qualitatively, what we can see is that the normal albedo for the colder samples on the left appear to be relatively brighter or higher albedo than the globes on the right, where we had warmer temperatures. There's a variety of ways you can look at this data just qualitatively. So another way I like to do it is look at maps as we step through time. So on the upper right here, we have a time tracker of local time. So as we step through, we're essentially increasing temperature, starting at warm, warmer, warmest, warm. So as I step through at this time, I'd like to draw your attention to this red square, and we can pay attention to the normal albedo and how that changes with temperature. So I like to think of it as starting at bright, darker, darkest, dark. And again, one more time, starting at bright, darker, darkest, dark. And so now really being able to quantitatively analyze these changes is something we're interested in. So this is my watermelon plot, I like to say. But essentially what it's illustrating is the overall change in reflectance per temperature. And so regions where this relationship was negative are shown in pink, and anywhere we had a positive change is shown in green. And I'd just like to point out that the green edges are really an artifact of the data we could see in some of the earlier plots. And so this is actually illustrating that over the majority of the surface, we're looking at this negative change in reflectance with an increase in temperature. And so here I've changed the scale where we're basically trying to highlight the regions where this change is greatest. And so those are highlighted in the yellow color, where we have the greatest change in albedo with temperature. And so there are a couple of main conclusions we can see with this plot. The first is that LOLA appears to measure a higher surface reflectance when the temperatures are colder. So again, that's at the 7-8 a.m. range. But overall, this change is very, very small. It's only typically about 1 to 2% change. Overall, that delta R, delta T relationship is ranging from 0, so no change, to -1. And this is multiplied by a factor of 1,000. As I sort of started the talk, one of our interests in looking at this was thinking about the mineralogy of the lunar surface and if these temperature-dependent spectral changes might be correlated with the mineralogy of the surface. So now below this plot, I've shown the orthopyroxene map for the moon by Lamellin's work. We're looking at the same spatial projection and spatial ranges. And so qualitatively, maybe there's some sort of correlation between where we see those larger change in reflectance and temperature, which again are in yellow, and where we have increased areas of orthopyroxene. But quantitating this relationship is something we're working on now and trying to understand any inherent instrument effects that will also be picked up in this analysis. So that's very much ongoing analysis. So overall, to conclude, we do appear to observe a higher albedo as measured by LOLA when the temperature of the moon is lower. This is consistent with the laboratory measurements of pure minerals, which I started out showing. It's also consistent with ground and spacecraft observations of other airless bodies. But overall, the magnitude of this change appears to be very, very low, on the order of a few percent, 1 to 2% really, this is due to the fact that there are lots of other minerals mixed on the surface and some space weathering effects that dilute this strong temperature spectral relationship. And ongoing work is focused on determining the root of these changes, how it relates to the mineralogy of the surface, how it relates with systematic instrument artifacts. But we're really interested in this idea when thinking about future science of and from the moon. There's been a lot of talk this meeting about volatiles on the moon and other airless bodies, and lots of times our evidence for frost or for ice comes from surface reflectance or enhanced reflectance. So as we're able to get more precise and more high-resolution observations in the future, it's really important to think about how temperature can influence our measurements. Thank you.
All right, are there any questions?
So, thank you. On the first thinking, it totally escapes me. What's the physics? Why is the the albedo changing with temperature? And then, one possible way out to me is do you have a plot of the instrument temperature? What else is changing at the same time?
Yeah, so to touch on the first part of your question, as the temperature is decreasing, we actually have a site contraction, and so this causes an increase in the crystal field splitting energy, which can increase the reflectance of the measured sample. So this is explained in detail in some of the early papers by Singer and Rausch, who did these really fundamental experiments that I showed at the beginning. And then your second question about the temperature of the instrument. No, it does not seem to be correlated. All the data that we're working with has been calibrated to take out any of those effects. So, yeah.
Anyone else?
I have a quick question. So to me, it looked like on your plot, the dichotomy that you were showing was mostly differences in albedo. And so it looked like the Maria had smaller changes than the Highlands, and that the biggest difference between those two is the albedo. And so how can you also pull out the albedo effects of what you're seeing and really understand how independent of a measurement you're seeing?
Yeah, that's a great point. So what we're doing is looking at the relative change by taking into account the intrinsic reflectance properties of these different materials, because that's really important to understand. So we're doing that with both the albedo of these different units and then also a lot of the work by Lamellin et al. Looking at the different mineral abundance. Thank you.
All right, if there's no more questions, let's thank Ariel again. All right, our next speaker is Christopher Kramer, who will be talking about discrete spectral absorption bands in 4 to 8 micron infrared region, new tool for remote compositional assessment of olivine Fe content.
Thanks for the introduction, and thanks to all of you for being here. Today I'm going to talk about some exciting possibilities for constraining the chemistry of olivine from spectra measured in a region of the infrared that for a while has remained fairly unexplored. So the composition of olivine, as well as those of other major rock-forming silicates, fundamentally informs our models of the origin and evolution of planetary crusts. Unfortunately, for a variety of reasons, it has been difficult to interpret the magnesium numbers of olivine in remote sensing data gathered from other planets and planetary bodies, including the moon. And one of the reasons for this is that in visible near-infrared spectra, there are overlapping absorptions that can hamper confident and precise interpretations of magnesium number. And so I think that one possibility for getting a better handle on this question is to look at a region of the infrared that for a long time has not been examined in close detail. So when we think about the visible and infrared spectral range that is relevant to remote compositional sensing, we think about the visible near-infrared, or V-near, and in the mid-IR. And so the visible near-infrared, shown on the left, is dominated by spectral bands that arise from electronic transitions in crystals, and this regime is also dominated by the scattering of photons, namely body scattering of photons. While in the mid-infrared, we observe spectral bands that arise predominantly by molecular vibrations, and that is dominated by surface scattering and thermal emission of photons. And what we have and also just to sort of elucidate, this is a generally sort of schematic plot where on the top axis we have wavelength, and on the left axis we have reflectance. And so what I am going to talk about here is the possibility for using a region of the infrared that I'll nickname the crossover region that is basically right between these two fairly different regions of the V-near and the mid-infrared. So previous work done by John Salisbury and others has indicated that in powdered samples of rocky materials, that olivine and some other silicates exhibit strong, distinct, discrete bands in the approximately 4 to 8 micron region, or also shown in wave number on this plot. Just the same, this highlighted box is the same as in the previous one. And so the bands in this region are generally understood to arise as overtone and combination bands of fundamentals that occur at longer wavelengths or lower wave numbers, and namely arise as overtone and combinations of fundamental stretching and bending modes, which are indicated on the plot with the key as shown there. And what's particularly exciting is that the fundamentals of these bands, as shown by Vicki Hamilton and Melissa Lane and others, exhibit systematic changes in their band positions with respect to magnesium and iron chemistry of olivine. And so then the major question in this study is what changes do we observe in the band positions of olivine with respect to magnesium iron chemistry, and how do natural and synthetic pure samples compare to each other? So to that end, what I've done in this study, along with my co-authors, is compiled data from two major sources. First, the Relab database and the USGS Spectral Library. We compiled data from multiple suites of olivine spanning, for the most part, the full magnesium iron solid solution series from force right 0 to force right 100. And all the data here are shown in reflectance. All these data were measured in reflectance, and that's a point I'll touch on at the end. And the spectra are offset for clarity. And all these are measured on FTIR. So the first thing that we see when we look at this, what we're looking at here is first a suite of what are referred to as the SUNY suite of synthetic olivines. They're some of the purest synthetic olivines that you can get, where I mean purity with respect to cation substitutions. And so what we see right off the bat is that here where the blue is the magnesium end member and red is the iron end member, we see two major strong bands that comprise a doublet that shifts systematically to longer wavelengths or lower wave number with increasing iron content. So when we then draw in the data from another well-known, well-characterized suite of olivines described by Darby Dyer, the so-called Bristol suite, which has more stoichiometric contamination, including oxidized iron. We see a similar trend. And an important thing to note is that the positions of those vertical dashed lines are consistent throughout the remainder of these plots, and that the blue and red values correspond absolutely with the relative abundance of magnesium. So it's also exciting that we see this consistency in trends, even though there are sometimes considerable impurities in these other synthetic olivines. So that was pretty exciting when we first saw that. The thing that we wanted to next see was, does this pattern that exists in natural olivines or in synthetic olivines also exist in a messier reality? So to this end, we compiled data from the USGS Spectral Library, and these olivines come from a variety of sources. The data are a little bit noisier, but what we see right off the bat is that there is a similar systematic relationship with the band position of the 5.6 and 6 micron bands and the iron composition. And also, as sort of a minor note, we can also note there are these sort of minor bands that exist in the synthetic suite that also exist in the natural suites as well. So that was pretty exciting. And then the next question is, well, we have natural samples and synthetic samples. We also would like to look at extraterrestrial samples if we'd like to potentially see this applied to other planetary bodies. So we compiled data from the Relab Spectral Library, and also just for note, one important thing to note that I didn't explicitly say before is that those data were all measured on powdered samples of varying grain sizes, but in the main less than 75 microns. And the same, for the most part, applies to the samples I'm showing here with some caveats. So what I've done here is I've compiled data from olivines extracted from meteoritic samples from Mars, shown in red, and 2 Apollo samples, shown in green and orange. The green colored sample is an olivine separate prepared by Peter Isaacson that comes from a basaltic composition sample. And then the orange glass is sort of the orange glass of great Apollo 17 renown. And one thing that's interesting to note is that not only do we see the same doublet that we saw before, we also see that while absorptions that would be strongly diagnostic of olivine are missing from the orange glass in the visible near infrared in the plot shown on the left, in the plot on the right, we can see the same familiar 5.6 and 6 micron bands, which likely arise from olivine phenocrysts that have been observed and characterized in the orange glass beads. So this was all interesting and very promising. The question now is, now that I've shown you all these plots, how do the band positions actually line up between samples of different provenance? So what I've done here is I've prepared 2 plots, and I'll show you them one at a time. Both plots show the position of each band, in this case first the 5.6 micron band with respect to olivine composition, and then I've plotted this up in wave number. And then the colors of the plot of the different symbols corresponds with the different suite or planetary provenance of the material. And so we can observe a couple things first, which is that when we plot the data up in this space, there is still this strong systematic relationship that is also monotonic between magnesium number or iron composition and the band position of the 5.6 band. And then what I've done here is I've plotted up 2 linear regressions with a breaking slope at about forced right 70. The linear regressions are fit to the data from the SUNY suite because that was sort of the nominally purest suite of samples that I had. The break-in slope is based off of first just an observation that there's a subtle difference in slope, but at around 4 straight 70. This is also based off of observations that, from Melissa Lane's infrared data, that there's a break-in slope around this 0.2 in this plotting space. So the other thing that we see is that for both the 5.6 micron band and the 6 micron band, that there's also a strong degree of similarity between the band minimum positions of the synthetic data of the synthetic suites and the natural suites. And then one thing I also wanted to mention that I didn't point out before is that I put error bars on the 2 Apollo samples because there's a range of compositions that are given for these samples where the likeliest composition is highlighted in the darkest green. So what I want to, so the key takeaways from this are that band depth and position, but especially band position, very systematically with iron content and olivine in this 4 to 8 micron spectral crossover region of the infrared. And I think that this spectral range is promising for remote sensing analysis of olivine composition and potentially other silicates, pyroxene and plagioclase, which are currently under study. And one other thing that I think is especially important to take note is that as detectors potentially come under development for this region for the prominent 6 micron band, it's important to understand what other silicate-related bands might be superimposed on this for understanding volatile distribution on the moon and other bodies. And then just some next steps include further characterization of olivine and then a suite of Apollo samples plus pyroxene and plagioclase. So I'll leave this up here just as sort of some food for thought, and I gladly welcome any questions or comments you may have. Thank you.
Hi, Chris. Paul Lucy, University of Hawaii. I noticed your spectra that you showed, some of them had very strong 3 micron bands. How can you exclude some of these features being due to molecular water?
Oh, the 3 micron features? In which plot are you referring to? 3 microns?
One of your early plots you showed the near infrared. So this one you have prominent 3 micron bands in the left, which suggests that if there's molecular water present, it would be exhibited at 6 microns. So how can you exclude water as contaminating your results?
Yeah, that's a good question. So so first off, the thing to note is that these are just spectra that I pulled sort of schematically and are not representative. These spectra are actually not examined in these plots later on. It's just sort of for demonstration purposes. In order to make sure that I was not including any sort of water bands in these data, I looked at the 3 micron band just basically to see is there something that sort of qualitatively and subjectively I would say constitutes a strong 6 micron feature. Mm-hmm. The other thing that that can be taken as some reassurance that the water is not a major contribution is that where the 6 micron band is that the 6 micron band itself shifts systematically with iron composition, which we would not expect in the absence of a strong silicon-oxygen bond-related feature. Yeah. Thank you.
Good answer.
Got time for one more if anyone has a question. Okay, well, if there's no more questions, let's thank our speaker again.
Thanks very much.
All right, our final speaker for this session will be Bob McDowell, who will be talking about the lunar payload for radio wave observations at the lunar surface of the photoelectron sheath, or ROLSes.
Okay. You people need to get out of here in 15 minutes, so let's go. This presentation is about a NASA-provided lunar payload that we're developing to make measurements of the photoelectron sheath at the lunar surface, which has the acronym ROLSes, and it sort of follows other activities that, this doesn't work. This, the co-Is and collaborators listed there include Jack Burns, and Jack's NASA Lunar Science Institute and survey teams have worked on lunar radio observatories for a long time, but years ago they didn't get funded. However, now things have changed, so hopefully there will be some interesting things. And ROLS is, of course, is a 10-day mission, so there's only a finite amount of result, but let's look and see what it will be. No? Yes. Okay, so we'll have an introduction and look at the science and technical objectives and the hardware review, and then you'll go out the door. As a status, well, the proposal referred to the stereo spacecraft WAVES instrument. But we're building the digital electronics using the design of the Global Ecosystem Dynamics Investigation Board, which is an experiment on the International Space Station. Frequency range of 10 kilohertz to 30 megahertz. But these high frequencies are intended to provide support for other lunar radio mission proposals. There are four monopoles on this lander. In the figure, you see these brown stacer antennas, and the commercial lander that is supposed to take ROLSes to the lunar surface is the Nova C provided by Intuitive Machines, and the landing site would be their landing site is in Oceanus Procellarum. Don't do that. Now what? That works that way. Now that wants to work, but that's not what I want you to do. Why are we going the wrong way?
It should be the big button is to go forward.
Oh, that's the button.
Yeah.
Is that right?
Yeah.
Thank you. Okay. Multiple funny things. Anyway, so the rectangle there shows Oceanus Procellarum. And moving on, the lunar surface photoelectron sheath has been modeled by using various simulations. In the one shown here, from a model from Pape and Horiani. You see the results for plasma at different times, and solar wind after a shock has gone by, after a solar flare, in the environment of a CME, and you see that it does have a substantial change for the density, order of magnitude. Well, in 10 days, we don't know how much of that we'll see, but we hope to see something. In any case, at 1 meter, the density is about 10 to the 7th electrons per meter cubed, which is a frequency of about 64 kilohertz. Here's a different model from code from Mike Zimmerman, and if you had memorized the plot from the previous page, you'll see that this one is somewhat different, but the results are not dramatically different in the sense that here, at 1 meter height, it's the density is 3 times 10 to the 7th per meter cubed. So ROLS wants to measure these values, and just based on the thermal noise spectrum, possibly on wave activity at the electron plasma frequency, and by absorption of the radio spectra of remote radio sources at frequencies at and below the electron plasma frequency. So other things that we will see from the lunar surface are radio sources elsewhere. In this plot, which is 24 hours of data covering 0.01 to 10 megahertz from the WIND spacecraft WAVES instrument, it shows, to first approximation, what ROLSes we'll see from the lunar surface. There is, one thing we will see is the radio emission from the Earth's magnetosphere, auroral kilometric radiation. We'll see solar radio bursts. We might see Jupiter. And wind at this point, as it has been for the last 20 years, is out at the L1, the solar Earth L1 Lagrangian point. So the RFI from Earth that it sees is quite weak, but it still sees some. Another phenomenon that we might detect is radio astronomy instruments on spacecraft typically detect dust when the particles strike the antennas or strike the spacecraft, because the impact releases electrons and ions from the surface, which affects the photoelectron environment and creates electrical signals that are readily detectable. And in this plot from Cassini, you see what the radio instrument sees when it flies through through Saturn's F-ring. So Rolls's might detect dust impacts on the lander or on the antennas if it's a cloud. Our time resolution is not designed to detect individual dust particles, but it could detect clouds of dust. So one more thing that we are considering that we might see is the radio waves coming down from whatever sources are out there, especially the more intense sources, will likely penetrate the lunar surface, and they might be reflected back up so that you detect them. And this tells you something about the surface below the lander. A better example is the Apollo 17 Lunar Surface Electrical Properties SEP instrument that made such instruments at 6 frequencies. There was a signal generator that created the radio waves, and then the detector was on the rover, so that they made measurements at various distances from the signal generator. And the Icarus article by Grimm describes the recent analysis of these results, and because no deep interfaces were detected, the thickness of the torus littrow volcanic fill where the rover was moving around must exceed at least 1.6 kilometers and possibly twice that. So reflections can give you useful data. One technical result that we want to obtain is what is the current level of terrestrial radio frequency interference. In this shown in this plot, you see a 24-hour plot from the wind waves instrument, and again the frequencies from less than 1 over 10 megahertz. And so except for a few weak solar radio bursts here, this is during solar minimum in 1999, on April the 2nd, when the WindWave spacecraft flew very near the moon. You see all of these transmissions coming up from the Earth, and it's a considerable amount of RFI, which would be a major noise source for a near-side lunar surface-based radio observatory, although we believe that we could still image solar radio bursts because they are very intense, and you'd have to just remove the noise from the source. So anyway, we would like to know how much that noise spectrum of terrestrial radio frequency interference has changed since 1999. So very quickly, this is the diagram. So we have antennas and preamps, and then antenna deployment electronics, and data processing electronics, and power regulation electronics, and possibly a cooling system, because on these landers the electronics get to see the lunar surface, so they may get quite warm. Our thermal engineer is working on this at the present time. Okay, some of you will want to know these things, but let me just point out again that the frequency coverage is 10 kilohertz to 30 megahertz, and we'll be getting data at about 17 kilobits per second, so it will be a good set of data. This is the electronics board from the Global Environment Dynamics Investigation. It's actually a LiDAR experiment on the International Space Station, so the daughter board at the front of the electronics will have to change, because our frequencies are a lot lower than LiDAR. But our engineers at Goddard want to use the same system. The data acquisition will take place in 2 bands. 10 kilohertz to 1 megahertz and 300 kilohertz to 30 megahertz, with the overlap helping to confirm calibration. And it will be analyzed using a spectrometer device that the engineering people at Goddard like. The frequency band resolutions are indicated. As I said before, this time resolution will probably be 5 seconds, although since Intuitive Machines has more communication volume available, we might be able to do a higher time resolution. So the schedule is, we need to deliver, well, we plan to deliver in July of next year, or at least by August of next year. And then Intuitive Machines would launch on spin principle at 7/16 in 2021 and land on the moon on July 22. So, in summary, the roles NASA-provided lunar payload will focus on determining the density and scale height of the photoelectron sheath, as well as detection of solar and terrestrial radio bursts, to demonstrate that could be done from the lunar surface, and the possible detection of clouds of dust impacting the system, and the current level of terrestrial RFI from ground-based radio transmitters, and maybe we might see reflection of incoming radio waves from the lunar surface or below the lunar surface. So anyway, we're looking forward to delivering rolls next year and obtaining data from the lunar surface in 2021. Thank you.
Any questions? I guess I'm curious why the 10-day mission lifetime was chosen. I mean, was that all you need, or is there some sort of limiting factor for that?
Well, this is a factor for all of the commercial landers at this point. They are, although they're pondering the possibility, they are not designed to survive lunar night. So they will try to land you as close as possible to dawn, and so you'll survive, the lander and the instruments will survive past dusk. So it could be a little more than 10 days, depending on where they land and so forth. But and also how quickly the thermal environment succeeds in destroying everything. But without a design to survive lunar night, it's a approximately 10-day mission. Yeah. So. That's actually there have been, of course, conferences on the subject of surviving lunar night, and it is an important activity to be worked. I mean, there are simple ways to do it, but it requires too much battery mass or radioisotope thermal generators, so that it's not simple. It is. The nature of the moon, with its very slow rotation, complicates long-term survival.
So I was just wondering if the local topography of your landing site could have a measurable effect on the measurements you're making.
Yes, I think in general that is true. We can go forward with Oceanus Procellarum, but different at different locations on the surface the photoelectron sheath density and scale height will actually be different. So you're not providing universal measurements. Any comments, Bill?
Sounds good to me, Bob.
Okay.
Okay, I think we're out of time, so let's give Bob another round of applause.
So Christina asked us to give a quick announcement. For those of you that want to leave your bags here and not take them on the buses with you, you can leave them in the main conference room, and that room is going to be locked. And then when we all come back on the buses, they'll unlock that room and you can recover your bags and such.